Hi, my name is Jim and today's topic is noise, and noise is everywhere. You can turn on the television, you hear it all the time. 0% APR, an SUV that's best in its class, approved by doctors, by medical doctors I wonder. So the same is true in electronics, and it affects analog and digital signals in the same way, which is, well, bad. So let's discuss noise a little bit and all of its undertakings here. So noise can be defined as any undesirable energy that falls within the passband of the signal. And there are several types. One is out-of-band noise, and this can be eliminated by filtering. An example of that would be people that live around Seven Hills, where a lot of radio and TV station transmitters locate, oftentimes can hear music and voice on their telephones. So the telephone company simply installs a filter where the wires come into their house, and it takes care of that. Now the reason that happens is there's some nonlinearity, a little copper oxide somewhere or something, that allows those signals, which are much higher than what we can hear, be decoded. So that would be an example of out-of-band noise. And noise affects, like I said before, analog signals, and basically it impairs the information. You have noisy audio, and if you're watching older TV, snow in the picture, which you can still see in digital TV if it was mastered in analog. Hum and audio. Hum is an undesirable signal, so it's considered as noise. And it affects digital signals by introducing bit errors. And there's a couple of different strategies to deal with that, but digital is not immune from it. So the types of noise are the correlated types, and those depend upon the presence of the signal. And if the signal goes away, the noise goes away also. Now, I may seem a little bit strange, but we'll talk about some of the vehicles that make that happen a little bit later. And then we have uncorrelated noise, where it's always going to be there whether we have signal or not. Noise sources: external, atmospheric noise, for example, lightning. Extraterrestrial noise, things that happen in outer space. Solar, the sun. Downlink shines into the sun like twice a year. It wipes out cable TV. So the sun is just filled with radio frequency energy, which includes, of course, the light spectrum. Cosmic noise. Some years ago, that happened in the United States, and it's believed to be a proton traveling at near the speed of light that had the energy of a tennis ball traveling at 60 miles an hour, which caused some concern. You feel it was slung around the star to get that kind of velocity. Background radiation, human-made noise, car ignitions, flipping lights on and off, electric drills, and so forth. There's also internal noise, and by internal I mean relative to electronics. And we have shot noise, which is a random variation in current flow. So if we elect to insert 5 electrons evenly timed into a conductor, they may come out kind of bunched up a little bit here and there, and that is a difference of arrival time, and the current therefore is altered, and that can be a source of noise. We have transient time noise. Modulated carriers suffer delay in transistors at high frequencies, so they arrive at different times, and that can cause some problems. And then we have thermal noise, which is everywhere except at absolute zero. That's 0 Kelvin. And this is caused by a random motion of electrons because they're experiencing thermal energy. They're above the absolute value of 0 degrees, and therefore move around with the energy. And this is also called Johnson noise. And if we were to look at this in a wire, as what we would see would be some noise voltage, and the average is 0 volts. So we can't claim any energy out of this. And we're going to look into this a little bit further in some detail. So those are some of the noise sources. And let's talk about the thermal noise a little bit. And the equation is relatively straightforward. It's N in watts. Got to remember that. The unit of that is the watt, equals kTB, where K is Boltzmann's constant. Now that equals 1.38 e to the negative 23 joules, which is a unit of energy per degree Kelvin. So that's a constant. And next component in our equation is the temperature in Kelvin. So the higher the temperature is, the more agitated the electrons become, and hence the higher the noise. And the third is B, the bandwidth in hertz. So if we're looking at a really, really wide spectrum, we're going to be picking up more noise because the noise is evenly distributed across the spectrum. So by making the bandwidth as narrow as it needs to be, we can cut down on noise. Now, in communications theory, if the bandwidth is 0, you cannot send any information. So we have practical limits on what we can do with that. Now we're going to take these apart from the standpoint of units and make sure that it makes sense to us. And I'm going to replace hertz, which is a contemporary term, relatively new, with its older term, which is cycles per second. Now what you have to remember here is cycles is a number. It does not have a unit. So if we write this out, N in watts equals kTB, K is joules per Kelvin, T is in Kelvin, so these two divide out. We end up with a bandwidth in cycles per second. Now if we take a look at this, we end up with joules, and yes, times cycles per second, and we can decompose a joule into a watt second. Not per second, a watt second. If we make that substitution, as what we see here, is the units of seconds divide out, and we're left with watts times cycles. Cycle doesn't have a unit, so the ending unit here is in watts. Exactly what we need. Now, when I first looked at this, I was wondering how you get watts out of this stuff, kTB, and that's why I decomposed it here, is for my own edification, and in fact understood what it was about. So, let's fix this right here. dBm. We can also express noise in dBm, and if you remember what the reference for dBm is it's 1 milliwatt. So we'd set this up as 10 because we're dealing with a power, and take our N, kTB, divided by 1 milliwatt and 10 times the log of it. So we can express that noise in either the linear domain, watts, or in the log domain, dBm. So thermal noise is continuous. It occurs at all frequencies. It's predictable. We mathematically know what it's going to be. It's additive. That is, if you go through another amplifier, you're going to add noise to the signal, and present in all electric devices, assuming that they operate above absolute zero. So we're going to use a resistor model here to try to figure this out. And what we have here is a noise source Vn, which is actually a thermal source, but we've mimicked this by using a voltage source so we can analyze this. And what we know for a perfect power transfer, or a maximum power transfer, is that the internal resistance of the source has to be equal to the load resistance. So these two guys are equal in our model here. And then what we see is, since these resistors are equal, we end up with a voltage divider, where half the voltage is across this resistor and half is lost across the internal resistor of our model. So now if we do a little substitution here, N equals kTB, and substitute in V divided by 2, quantity squared, over R, and set that equal to kTB, we can kind of then clear things out here by multiplying 4 by 4, and then we end up with is V noise squared divided by 4 times R. Setting these equal and solving for V, we end up with V squared equals 4R kTB, and then taking the root of both sides, the V noise is equal to the square root of 4R kTB, or it's equal to 4R times N, which is equal to kTB. So what we can conclude from this is that the noise voltage is inversely proportional to the square root of the resistance. So that's kind of the way the model was developed. It's kind of good background, I suppose. So let's consider this. You might be thinking, well, if I make my resistance real low, then I'm going to have low noise. And that kind of makes sense, sort of. Problem is that Pn is going to be determined by two factors, and that's going to be the bandwidth, and it's going to be the temperature. That's that. So if we further decompose this, we could say that P noise is equal to V noise times I noise, and then conclude from that that the higher the resistance, the noise is going to be high, but the current is going to be low because Pn is constant. Or if we lower the resistance, the voltage will be low, but the current will be high. The noise current will be high. Because the product of the two of them have to be constant. So in current devices like transistors, noise current is just as damaging as noise voltage, say, in a voltage controlled device like a field effect transistor. So we can't make it go away by wiggling resistors. Now let's work an example here. We have an audio amplifier, we'll say with a bandwidth of 20 kilohertz, and that usually starts kind of low, say 20 hertz or 25 hertz up. So I'm just saying that the overall bandwidth will call 20 kilohertz, and some humans can actually hear above 20 kilohertz, which is interesting. And we're going to connect the input to a 1K resistor, and we're at room temperature here, we'll say at 73 degrees F. And what is the noise voltage that's caused by the resistor at the input to the amp? Now later we'll discuss what the amp is going to do as far as noise is concerned, but right now all we're looking for is just the noise from the resistor. So first order of business is to get the temperature from Fahrenheit into Kelvin. I'm going to do that in two steps. First I'll convert it to Celsius, F minus 32 degrees times the fraction 5 over 9, and that comes out to be 27.7 repeat degrees Celsius. And next, to convert it into Kelvin, I take the degrees Celsius and add to it 273.15 degrees. So that's going to be the difference between 0 degrees Celsius and 0 Kelvin. And that comes out to be 295.93 Kelvin. And you don't use the little circle symbol with Kelvin. You use it with degrees F and Celsius. So, N equals KTV, and then plugging in our numbers here, we find that N comes out to 81.73 e to the negative 18 watts. And that would be called 81.73 atto watts. Atto is the SI prefix for negative 18, and femto would be negative 15. Now that sure seems low, but things add up. So if we wanted to convert that into dBm, we would just use our 10 log operator relative to 1 millivolt again, and we see that that would come out to be negative, kind of important, negative 130.87 dBm. So there we have the power expressed in the linear domain and also in the log domain. So if we wanted to find the noise voltage, I'll just say Vn is the square root of 4R times N, and working that out gives me 571.8 nanovolt. So that would be the actual voltage, and this would be, by the way, in RMS. Not that that would matter much with uncorrelated noise, but the noise power is average power. It's not anything to do with peak. So getting back to noise again, let's talk about correlated noise. It's present with signal. Why is that? Well, if there's some nonlinearities in the electronics, and there's nonlinearities everywhere, caused by, say, harmonics, some distortion, dielectric absorption. Printed circuit boards and capacitors actually absorb energy, and when you discharge the capacitor for a minute and walk away and come back 10 minutes later, there'll be voltage across it, called dielectric absorption, and it's really not nice. It causes things like distortion. We have aliasing, if we're sampling a digital signal, the content of the signal has to be less than half of the sample rate. Otherwise, frequencies are aliased back into the band. For example, if you talk outside of your exchange on a telephone, your voice is being sampled 8,000 times a second, and the highest frequency that can be transmitted is 4K, and the telephone company typically limits that to 3.3. If anything above 4K were to be sampled, that would be imaged. For example, a 5K signal would be heard as a 3K at the receive side. Now, the bad thing about aliasing is you can never ever get rid of it. So there's some heavy-duty filtering that has to go on before you sample a signal. You watch westerns and you see wagon wheels turning, stagecoaches, and they're slowing down. You might notice the spokes come to a stop and then start to turn backward, come to a stop, start to turn forward and stop again. That's aliasing distortion. And what's being sampled? The shutter on the camera. So it's not only involving electronics. So next we'll go to signal to noise power, keyword ratio. Abbreviated S to N is equal to power signal divided by power noise, and the higher the ratio the better. So we want a good S to N, and we can also express this in decibels just by taking the log, 10 times the log of the signal power divided by the N power. Sometimes we see this, S plus N to N, and the interesting inference here is that we can measure the signal without noise. We can't do that. It's always going to have some kind of noise. But if you see this here, what it actually does for reasonable values of N, it converges upon S to N for reasonable values of N. See here, noise factor and noise figure. Well, these are used to determine how much a signal deteriorates if it's passed through some equipment, and it's not too bad. The noise factor, F, is simply the S to N of the input divided by the signal to noise of the output. And remember, the signal to noise of the input is going to be larger than the signal to noise of the output. Now, the signal may be higher at the output, but the equipment is going to degrade the S to N. Therefore, this is going to be a number which is greater than 1. Secondly, we have noise factor, which is just a way of expressing noise figure in decibels. And it's 10 times the log of F, which is same as 10 times the log of the S to N ratio of the input divided by the S to N ratio of the output. So we'll stop here. We have more noise to talk about, and we'll do that in part 2. And thank you for watching.